Swayam Prabha. Digital India. Educated India.
Welcome everybody. Today we are going to discuss a very important modern pump known as turbomolecular pump. As the name itself suggests, it is looking like a turbine and it pumps molecules. That means the pump is going to be used in molecular flow. When we get molecular flow in vacuum systems, when mean free path is quite longer compared to the dimensions of the chamber or dimensions of the flow channel, etc. This normally happens in a typical systems below 10 power minus 3 torr. That is why we call it as starting point of high vacuum, and above that it is medium vacuum and poor vacuum, for which rotary vane pump and other pumps which we have seen in last few classes. So, this turbomolecular pump comes under high and ultra high vacuum. For many applications people use it just for high vacuum from minus 3 to minus 7, but with some precautions these pumps can be used to produce 10 power minus 10 like that. And where are these applications? In modern semiconductor industries, nuclear physics, particle accelerators and space simulation chambers, metallurgical applications, cryogenic applications. Wherever we require high and ultra high vacuum and also good pumping speed and a neat clean vacuum without much of problems like water cooling system, etc., and a compact. So, this combination is possible only if you use turbomolecular pumps. So, in this lecture we will be covering the introduction to turbomolecular pump, its construction like various blades and bearings and motor coupling, inlet, exhaust, various other small peripheral equipment associated with turbomolecular pump, backing ports, backing pumps, etc. Then we will see the operating principles of it. Later we will also see some limitations of pumping certain gases. And towards the end we will touch upon various applications and advantages of using this pump over other pumps, etc. Okay. Coming to the introduction of basic concepts associated with turbo pumps, most of you may be knowing that a fan rotates and it tries to compress, but actually it is blowing. That is for gas phenomena. Compression ratio is not much, but there are turbo compressors. Multiple stages will be there, various rotors containing some turbine blades and stators, again rotor, again stator. This sort of thing you will be seeing in turbo compressors, even in engines, in aeroplanes, etc. You will see such arrangements. So, basically the turbomolecular pump structure will look like this. There are series of turbines. These blue color things are turbines which rotate, and these red color things are stator type of things. They are also like turbine blades, turbines, but they do not rotate. They are supported from the casing in a static manner, and rotors are connected to a common shaft and thereby it rotates. So, this is nothing but multiple rotor stator combination, each is a turbo wheel. Okay. That is the construction aspect of it. But how do you produce vacuum? For that, let us start from a basic concept. Once the level of vacuum is already 10 power minus 3 torr, where the mean free path is quite longer compared to the dimensions, most of the molecules moving around, they will not hit each other, because mean free path is larger. They will hit mostly the walls, and in between if you keep some solid material, they will hit that. Molecules will be randomly moving. This random motion is associated with pressure. Okay, 1/3 mnc square bar is P type thing. A directed motion is related to velocity. At higher pressures, we have directed motion of the gas phase. In vacuum conditions, particularly high vacuum conditions, directional means molecules are being directed in a particular direction. The other day we have seen in ion pumps, molecules are directed using electric fields. Here, randomly molecules are moving in every direction, and in that direction where the pump is connected, the molecules are touching a high speed rotor and they will be baffled towards a direction, and the extra velocity or kinetic energy that it gets from this moving high speed blades, that will be again converted into random motion with a stator which does not rotate, a sort of breaking this, and in the process pressure builds up. Later another rotor will again give another impact to that. That way a series collisions by alternative rotors connected to a common shaft like this. All these red looking things are rotors, they are connected to a common shaft. Series of rotors interceived with series of stators creates compression as well as streaming from top to bottom. Why should we do it? Because below 10 power minus 3 torr, normal medium vacuum pumps cannot pump because of various limitations we have seen in rotary pump, etc. So, they need some molecular pump. Diffusion pump is also sort of molecular pump, but that works on oily substances, water cooling, etc. But in turbomolecular pump, we do not have that problem. It is a dry pump, it is an oil free pump. It is exactly this that has given it lot of importance. But the success came because of high speed rotation. Unless you rotate it to such a high speed, all these blue looking rotors, where the tip velocity is of the order of free molecules which are moving like this, you cannot impart any extra momentum to the molecules in a rarefied atmosphere. Coming back to our fundamental conceptual discussion, if a molecule in the molecular flow or in a rarefied atmosphere, I am not showing chamber, etc., you assume that it is already in minus 3 torr here, ambience. The molecule is moving randomly, and if it hits a surface, this arrow is a wall inside a vacuum chamber. If it hits, it will go back again. It is not like optical reflections, etc., because roughness is much more than the diameter of the molecules. It will go most likely in this direction. It can also go this way also, depending on where it hits and at that local point what is the surface profile of that roughness. But generally when it is reflected like that, at the same time if the wall itself is moving, then what will happen? it will add some additional velocity in the moving direction of the wall. So, this component of velocity is added, otherwise a random velocity which is getting reflected, that velocity gets additional velocity because of moving wall. You can create another moving wall here, like that. Multiple moving walls if you create, multiple times it can get velocity increment, but we have to see to that they are streamed into a forward direction towards 4 vacuum pump like diffusion pump. You cannot directly hit and send it to the backing pump. You have to convert that into pressure energy, thereby you will get some compression. After that again give velocity. Otherwise, once a high speed rotor hits and give velocity to that, next high speed rotor will not be able to give additional velocity. Why? Because this is a molecular flow. Molecule was hit by one rotor and it got already some additional momentum. So, the same additional momentum you cannot get again here. So, that additional momentum should be again randomized. That way, alternatively the stators will randomize this and convert that into a sort of pressure, and after that they redirect these molecules in such a way, because of molecular flow conditions or a rarefied conditions, the slots are cut in such a direction that the molecules which are hit by the first stage are going towards the second rotor only. That way you can adjust the angle with which they are bent, these blades, alternatively stator and rotor. So, basically we have to give a directional velocity with a high speed turbine equivalent to a moving wall, and it gives additional velocity, so that it will be picked up in a particular direction in addition to the random velocity. Okay. As I already told you, why should we do all these things? Because we need to have a clean vacuum, and we only have to have compression using a high speed rotor, which is supported on a shaft with magnetic bearings on top, and bottom there is an oil bearings, etc. We will see when it comes to the construction later. So, basically I want you to understand the random motion of the particle is changed to a directive motion by a rotor blade. This is followed by a reconversion back to the random motion by a stator blade bent in opposite direction to the rotor. You can get that feeling here. Okay. The slots are cut in such a way that the stator looks like a mirror image of the rotor, and entire ambience is already rarefied by a pre-evacuation, where lambda is much more than the dimensions of the pump. Then only it will be a molecular pump, otherwise it will be gas compressor. And since molecules are moving on an average in the axial direction, it is a sort of multi-stage axial compressor. But this is compressing molecules. But when they keep on compressing, when they come down, they will be coming to a higher pressure of 10 power minus 2 torque. You can connect a rotary pump and take it off. But rotary pump will have oil again. Some oil molecules may back diffuse. We will get oil contamination. So, dry pumps are available at 10 millibar. So, what they do is, below this they try to arrange one drag section. We will see that the drag compressor, in addition to this turbomolecular compressor, will increase this compression by another 100. So, that you will get 10 millibar. Afterwards, backing scroll pump or claw pump or dry membrane pump, such dry pumps operating at 10 millibar quite efficiently can take over. Of course, we have to see the throughput is conserved. S1 P1 on the top of the turbo pump should be same as bottom, that should be same as drag stage. After that, the backing pump, everywhere at every section, S1 at that point pumping speed and the P existing at that point, the product should be constant, sort of mass conservation that you have to see. Little bit closer look into the constructional aspect of it, you can get here. This is the most modern turbomolecular pump. I have taken it from Pfeiffer manual. In fact, original discoverers are from that company only of turbomolecular pump. Nowadays, lots of companies are manufacturing turbomolecular pumps. What is the difficulty in manufacturing? A top magnetic bearing is required, because you cannot have oil bearing here, and you also require a lubricating type of wick bearing here, and this is towards the 4 vacuum pump, like a diffusion pump 4 vacuum pump, and this is my drag section, which is also connected to the same shaft, and that is connected to an electric motor having high frequency power, because higher the frequency, rotational speed will be more, number of pole pairs also will be more. So, it is a very specialized motor, so that the rotational speed will approach even 60,000 rpm, 80,000 rpm, like that. Why this high speed? The tip speed should be of the order of free molecular velocity of the molecules which we are trying to pump. It may be nitrogen molecules, it may be oxygen molecules, it may be helium molecules or hydrogen molecules. Helium molecules are lighter, hydrogen molecules are still lighter. So, lighter the molecule, its free molecular velocity is very high, more than 1300, 1400 meters per second. Whereas, heavier molecules like nitrogen and oxygen, only 300, 400 type of things. Okay. So, the tip velocity r omega here, the linear velocity should be such that it should be of the order of 1000 meters per second type of thing. Then only it can give additional velocity component to the free molecular velocity if the molecules hit this fellow. And we have to adjust the slot directions and again stator directions in opposite direction, since in such a way slowly molecules are coming here, they are hit, they are baffled down, they are randomized, they are redirected through the stator, and again next rotor will hit, next stator will randomize and redirect, like that it will come. At this end, at 10 power minus 2 torr, a drag type of thing with slotted thing, it will rotate continuously like a snake, and the molecules little denser, by minus 1 torr it is already denser. These molecules, because of narrow gap between that and housing, it is sort of semi-continuum concept. So, that semi-continuum molecular gas will be dragged continuously as it comes down. That way it is called a drag pump, connected to the same shaft to the rotors of this turbomolecular pump. So, it contains magnetic bearing, centering piece, and then rotors, stators. The stators are supported from the housing, rotors are supported by the rotor connected to a high speed motor. So, when it comes to the bottom of the turbo pump, crossing all the rotor, stators and then drag section, finally it will come at a pressure of say 5 to 10 millibar. Then the 4 vacuum connection will be able to pump it out easily to atmosphere. In a way, it is a positive displacement pump. So, originally minus 3 torr has to be created by a backing pump, but that time it will be connected as a bypass mode, like our diffusion pump we have seen. I am not showing all that, because discussion is on turbomolecular pump. When we later go for system design, when we later go for applications, we will again come back to that. How do you produce minus 3 torr initially? How do you switch on, and how do you maintain backing vacuum? What sort of precautions you have to take with the combination of pumps, etc. We will again commit to that. So, even if you miss something here, we will again cover it there. That time we will call it as a vacuum system based on turbomolecular pump. Here I am talking a simple picture on turbomolecular pump construction and action principles. So, let us concentrate only on that aspect here. So, identify the components: rotors, stators, high vacuum connection. There will be very high vacuum, means it will be metal gasket. But we will see what is metal gasket later. If it is minus 6, minus 7 torr, you can have white on, like that. In the bottom, you can have a dry membrane pump or scroll pump or very large scale turbo pumps. Then you may have to have roots blower followed by some other dry pump like claw pump, etc. Or even I would say nowadays very high quality compressors are coming, screw pumps, very dry. So, if very large scale things, maybe you can also connect that type of things. Any one of these dry pumps, screw, scrawl or anybody can be connected here, and you have to see to that the S1 P1, that is the pumping speed here at that pressure of minus 7 torr multiplied by that pressure should be same as the 5 millibar or 8 millibar after this turbo molecular section and turbo drag section. That this vacuum level should be such that S2 P2 also should be same. That means continuity is maintained. And if you have 9 such stages, each having a compression ratio of 5 to the power of 9, compression ratio is very high. That is why using these pumps you can get 10 power minus 9, minus 10, but very costly pumps, because balancing has to be done when rotors are rotating at 80,000 RPM. But thrust is not much, because it is already rarefied gases, that you have to see. Turbo compressors thrust is very high, it is compressing gases there. So, motor and all very big motors, but here very small motor. Okay. So, torque is not that high, because they are only compressing molecules, but the way you maintain these gaps, the way you maintain oil free bearings, the way you bend all of them and balance rotors, the way you rotate them in such a way, in uniform compression takes place. When it comes down progressively higher and the higher pressure here at every stage, stage means one rotor and stator is called one stage. Towards bottom, mean free path is decreasing. So, that is why the gaps cannot be that high, that is why the bottom stage blades are bent in towards the horizontal plane, because the gaps should not be so big there, that precaution you have to take. And all the rotors are supported by the shaft, all the stators are supported by the housing. And there will be venting port, you have to slowly vent it, because such a high speed you cannot suddenly stop. So, you have to tangentially stop that, slow it down, switch off, it will take quite a lot of time. Even if you switch off the pump electrically, it will still rotate hours together. That is why you do not require a valve instantly to close, either this side or that side. To be on safe side, we will put a gate valve, that is a different thing for isolation, but generally it is not required also. That is one advantage also. But you have to see to that no dust or anything enters here, then it becomes a grinder. It is not a turbomolecular pump. With that construction, under molecular flow conditions, the velocity is approaching velocity of the tub, approaching the average velocity of the gases. We will have very high pressure differences across each stage, one stator and rotor, and with turbomolecular sections as well as drag sections, you will finally get around 10 power or around 10 millibar or 8 millibar, like that, at which you can easily suck it using available dry membrane pumps. If you want to have a 10 power minus 2 torr as it is without drag, then you should use a rotary type of pump with proper precautions taken for oil free contamination. You should not slowly diffuse back. Under molecular flow conditions, just because overall flow is one direction, there will be some return flow also, because molecules are independent. So, oil contamination is not allowed in semiconductor industry or some other industries. There you have to be careful. If your application is only a low pressure, it need not be clean vacuum, then you can use any backing pump. In fact, if you put rotary vane pump, you will get very good backing also. So, you will have to see that the S1 P1 should be same at the inlet of the turbo pump, should be same as S backing into P exhaust pressure, exhaust of the turbomolecular pump. Okay. That will be the inlet of the backing pump. So, at that inlet, if you further analyze, at the inlet, that S backing and P exhaust of the turbo should be same as atmospheric pressure again, because it will be finally compressed there. So, you have to maintain this SP products constant at every stage from ultra high vacuum to the exhaust. That is where the engineering challenges lie, and the real challenge is to make very high quality bearings and to balance these blades perfectly. If you do all that, you will get pumping speeds of 3500 liters per second, and you can produce 10 power minus 10 torque. Okay. And with the development of high quality magnetic bearings and very high quality power supplies, very high quality vacuum compatible motors, today these turbomolecular pumps are being used routinely in almost every industry. Even 10 power minus 5 torque you can easily get with diffusion pump. People want to be more comfortable in laboratory atmosphere in universities. They are also switching over to turbomolecular pumps. Actually, they do not need it. When we were students, we were using only diffusion pump. We produced 10 power minus 7 torque. Today, my students are using turbomolecular pump to produce minus 5 torque. But still, they want comfortable. They do not want water circulation, oiliness, etc. They will say clean vacuum. But some applications like cryogenic thermal insulation or anything, you do not require cleanliness. You require minus 5 torque, so that it is a thermally insulated. But still they use, because naturally people want comfort, convenience. So, engineering automatically, science becomes technology, technology becomes engineering. It comes, and naturally more and more comfort is required. But a real challenge of turbomolecular pump is still we have to develop in our country these pumps. It is not, they are not available. Whoever wants to make a startup in this, they should see to that high speed rotation, high speed turbine blades. But you need not worry, because these blades are not subjected to high pressures. So, you will not have much thrust. So, if you are very good precision machining, etc., balancing, you may be able to do, if not today, after a few years. This is one thing I want to suggest the would be future technologists and engineers in our country, because these pumps are being manufactured in various countries. Why not we also make it? This is one thing for the startup people. And when you observe the pumping speed, you will find various pumping speeds for various gases. That makes sense. For example, what you see here, hydrogen, its pumping speed is small. Why? Because it wants to pump. Lighter the molecule, I can heat it, but lighter the molecule, its velocity, free molecular velocity is very high. So, turbine tip velocity may not be that high. For a particular velocity of turbine blade, it can easily impart that extra velocity to nitrogen, not hydrogen. That is one problem. Hydrogen being small, when it comes this side, again it may go back through those gaps. So, all these problems, hydrogen catching is very tough. Very small fellows, catching them is very difficult. Okay? But big fellows, hitting them also difficult, you require more energy. So, with this you can think that depending on the gas, you may have different pumping speeds. If that pumping speeds are not good enough, you may have to use multiple pumps. If you use that, you will be able to get very good vacuum, and this vacuum is going to be dry vacuum pump. But lot more can be told on turbomolecular pumps, action, constructions, materials, bearings and precautions, etc. Lack of time, we will cover it when we make turbomolecular based systems for semiconductor manufacturing, etc., towards the end of this course. So, we will end this topic by listing out some applications of turbomolecular pumps, where they are now being routinely used, like semiconductor manufacturing equipment, deposition equipment, day to day life in laboratories for PVD, CVD, sputtering, etc., for coatings, engineering coatings, etc., analytical instruments like SEM, TEM and XPS, etc., they require ultra high vacuum. Otherwise, they cannot analyze surfaces. You will be analyzing a dirty surface, because a lot of monolayers are formed. So, you require, and etching you have to do under vacuum. So, under such instruments, they are all using, once upon a time they were using diffusion pumps, now they are using turbomolecular pumps. Similarly, particle accelerators, space simulators, flat panel display people who are manufacturing these screens and semiconducting devices, laptops and cell phones, they also use turbomolecular pumps. And if you go to any nuclear establishments, there will be series of turbomolecular pumps connected to a common manifolds. Okay. Similarly, space applications, you may have hundreds of pumps to evacuate large scale chambers. After initially hogging the whole chamber using some backing pump, which is also dry, like your any other claw pump or anything. So, how all these things are done, we will see when applications come. So, once we know that lot of applications are there, then only it is cost effective, otherwise it is not cost effective. So, say decision should be taken by the engineer whether to purchase this pump or not, that we will also cover in the next lecture, that is the end of this production time, where some sort of selection criteria of various pumps. But coming back to the turbo pumps, the advantages are roughing high vacuum valves are not necessary, because it rotates at high speed and keeps on rotating even if there is a power cut. And very dry pump, no contaminating coming from motive fluids or anything, even working fluids, or even any bearing lubricants, etc. Nothing is there on the high vacuum side, magnetic bearings. Less chance of backstreaming. So, quick startup and shutdown, that is the main advantage today people want, comfort. And low operating and maintenance expenses, provided you take care. If you put some dust or anything, you are in trouble. If it goes out, you have to replace it. You cannot repair it easily. The company people only have to come. It is not like opening a diffusion pump and cleaning and putting oil. It is little tough. Only experts can do it. You can also get trained, and little bit of maintenance you can do, but if it is replacing a rotor or anything, you cannot do. You have to alternatively adjust status with the housings neatly with gloves and in a neat room, arrange rotors, etc. And more predictable performance. But the disadvantage will always be there, of course, from cost point of view. But if your application is very high tech, cost does not matter, but that should be taken into account. Precision balancing. So, the engineers who design manufacturing or even who operate it must be aware of these things. And proper operation is important. Suddenly you expose it to atmosphere, such a high speed rotor, and it gets huge loading, then it may get jolting, and that will spoil. And if it little bend or something, and if it hits some other fellow, and it will at such a high speed, it will crack into pieces. Several such accidents took place in various laboratories, where they handle it with little careless manner. That is important. And they are not available in very large size, because larger the diameter, the balancing of these rotors is quite tough. You have to be very careful on that, otherwise it may have some bending. Okay. And pumping limitations for light gases are always there, because light gases velocities are much more. And finally, it requires skilled manpower. And if you can take care of all these things, definitely turbomolecular pumps are most modern pumps, dry pumps and high tech pumps, which are being routinely used with backing dry pumps with the addition of drag section. That way, if you multiple different let us say 100 turbomolecular pumps, you can connect them in parallel, then the effective pumping speed will be 100 times more. But backing, if you require more and more, then you may have to use roots blower, which is also dry, backed by another dry pump. So, you will have to design your system based on loading situations, based on pressure requirement, ultimate vacuum requirement. So, I leave it to the customer finally. So, that we will cover it, various applications, what type of combinations of turbomolecular pumps with various backing pumps are to be used when we discuss applications. So, today we have seen very high tech turbomolecular pump, rotating at very high speed, 1 lakh RPM type of thing, producing very dry, very good vacuum, ideal for ultra high vacuum situations in most modern industries, semiconducting, space and nuclear, even in metallurgical industries. Thank you very much.